Okay, welcome guys. So this video, let me just tell you guys that how to write Lorentz covariance of the Maxwell equation, and hopefully this is the step by step. Okay, although this is not so easy, and it's very easy but tedious, right? So let's denote the Minkowski space. Is just let's denote CT is x0 upper 0, x1 is x, y is just y, x2, z is just x3. And everybody knows different some people use different notations. Okay, some smart guy also put I here, so they're just stupid that there's I in the coefficient. Okay, so the Maxwell equation, what I want to use is this one. Okay, let me just quickly write down a stupid one. Okay, rho and B. Okay, so in this case, we are trying to first write down the wave equation and write down the electric field in terms of these stupid things. Okay, so we have a relationship like D equals to epsilon E and B equals to mu 0 H, right? So we are assuming that there's no other terms. Okay, and so it basically is in a vacuum. Okay, so the standard technique I don't want to mention, I think everyone knows about is that one can write B equals to gradient curl A, at least locally, and the E will be partial A, partial T, minus delta phi. And the reason is that since divergence of B is 0, so B can write as base curl 1, and this is come from this, right? So once you write that B as curl A here, and you can pull this out, you get curl something, you get curl E plus partial A partial T is some 0, right? So it's natural to write these things as some strange gradient. Okay. And then we added things called Lorentz gauge. Okay, so I will not talk about the detail of the gauge transformation, fiber bundle. I will not talk about this, but don't worry. Okay, so this is the relationship we want to add. So one can show this always work because there is a gauge transformation of A. Okay, and so now you have this, right? So we can pull. So we have already solved these two equations. Right. So the next we just pull these two. Right. These two are terrible one. Okay. So these things we get rho if you are very careful, and then you put D equals to epsilon E. Right. You just put this. Then you will get the square phi plus dot partial A partial T, which is minus rho epsilon. Okay, and so this is the first equation. Okay, and the delta H, right? You get the cross H, right? H is mu 0 B. So if you put this one, and the partial T partial D, right? So D now is terrible, another terrible thing. D is epsilon E. Okay, so this one plus rho V. What is this V? Okay, so V is some voila. Okay, so get this one, these two, right? And this is just partial the Laplace, this one. Okay. And so you can clear these things. You have A and T, right? So this one, right? You want to eliminate both two. And then there's a Lorentz so the Lorentz condition helps, right? Because for this one you get this partial A partial T, right? So this one is actually you can write it as partial A partial T dot A, and this dot A is just minus mu 0 epsilon 0 partial phi partial T. So the first equation is become only depending on phi. You get this one 1 over c squared partial T squared phi equals to this one. And why we have this? Because I use c squared equals 1 mu 0 epsilon 0. So you see, for the first one, this equation, since you denoted this, so this becomes this. Right, you just pull out the coefficient and yeah, you get this. And for this one, it's a little bit large, right? But we still don't worry and try to do it step by step. this video try to provide the details, right? Because if you go to see Wikipedia or something, that people always say, oh, this is correct, but somehow like nobody want to tell you all the details because it's tedious, right? But we can write something tedious on the YouTube. Okay, so sorry about that. So how to do this, right? So we got this, and hopefully we can eliminate these two, right? I write this dot a with this dot a with just partial mu 0 epsilon 0 partial phi partial t, and hopefully this term let me check. So I did something wrong, I think. So h no, sorry, yeah, sorry. So this is 1 over mu 0. Okay. So this term, actually this 1 over mu 0 term, let's see it very carefully. Oh, maybe this video should separate as two. Okay, so you pull out this one to this one, and you see and you see this one. So hopefully these two will cancel, right? These two will cancel, right? So indeed cancel. So finally you get this one, the Laplace A. You get 1 minus c squared partial t squared. You see this phi term cancel. Equals to minus mu 0, there mu 0 here, rho 0, rho v. Okay, nice. So we get the two equations. One is this, and one is this. Okay, so it's very happy that somehow everyone knows about how to do this. Okay, so yeah, so the next is very simple, right? So now we can write Laplace square minus 1 over c squared partial t squared as a partial mu. So the large partial mu is just 1 over c partial t, and the Laplacian, and the partial mu should be 1 over c partial t, negative here. And now we use the matrix as most minus term. Okay. So this is partial mu equals to something, right? So this is covariant form, because this is called Darlon version, right? Darlon version is invariant under Lorentz transformation. Okay, so that means the wave equation in a covariant form. Because one can write because I can denote A1, right, to be AX mu 0 C, and do the same thing for the A2 and the A3. But for the A0, lower 0, and upper 0, I denote it the same as epsilon phi. So basically, that means the phi and the A are like a 4 vector, and the wave equation can be just written as this 4 vector, right? Let's say large over 4 vector A mu, right? This is A mu as J mu. And what is J mu, right? J mu is just very easy. I just denote that J1 is just rho Vx divided by C, and then J2, follow the definition, is JVy divided by C. J3 is just rho Vz divided by C, and then J0 is just J0, right? J0 is just rho, right? Rho. I mean, if you see these 4 terms, right? There's a negative term, so I can just change this as J mu. J mu. Okay. Oh, wait. So I think from our definition, since there's a negative term, right? So maybe we use this one, this plus term, and this is minus. So the equation is this, and this is plus. So there's minus here. So the left hand side is negative partial square partial mu. So it's negative. So this is our convention. Sorry about this. So I think this is minus. This is correct, but this is minus. This is plus. Okay, so this is the. Okay, so let me just Let me just clear. So the final result will be this one is just partial mu, and this one is just okay. And the full vector is just phi a. I denoted the 0 as the first component, and the matrix partial mu is just the correct one is 1 over partial c plus. And for lower one is basically negative the time directions. So this one is correct. Okay, and the J mu just the row put in here, and up to some conventions that V C row. Okay. Then the wave equation is just Dalam wave equation is what? It's just this. So this is JV. Okay, so yeah, this is the wave equation in a covariant form. Or basically partial square. Okay. Nice. Okay, so then I think this is good for today. And the next time we just try to rewrite. So next time we will rewrite the Maxwell equation into partial into this one that and people like to tell about this one, or you put this in upper, right? Oh, so it should be yeah. And another is basically another we will write another is I think another is somehow like this one. So we will define what's still. So next time we just try to write the Maxwell equation into a covariant form. And the next time we will try to start from the Lagrangian, to find the Laplace equation, to find the Maxwell equation. Okay, so I think this is good for today, and I will see you guys in the next video.